So in this video, we're going to discuss critically damped RLC circuits. So remember that critical damping occurs when the damping factor alpha is equal to the resonant frequency omega naught. And under that scenario, if we think back to our quadratic characteristic equation, the two solutions to that equation are simply going to be the same real value repeated. And if we think about the general form that we assumed for the solution of the source-free RLC circuit up until now, it was the sum of two exponential terms, where the complex frequencies were actually the arguments within the exponential terms. So if those are the same actual value as would be the case in real repeated roots, they would merge into one single exponential. And under that scenario, you would still have that one unknown parameter that is set by the initial conditions. However, since this is a second order equation, it would need to satisfy two individual initial conditions. So what you have is an overdetermined system there, and the book does a nice job of showing how it results in a contradiction if you continue to assume the sum of two exponential forms. So what that means is that what we'll see, the general solution for a critical damped circuit has a different form. It has an additional factor of t, as those of you that have seen differential equations before probably remember. But one other point that I wanted to bring out is in practice, critical damping is incredibly hard to assume because you can kind of view it as a bit of a resonant condition. It's a very precise scenario where these parameter values actually satisfy alpha equals omega naught. Particularly, we can solve and show that the inductance in this case has to be the product of 4 times the resistance value squared times the capacitive value, even if you were to be able in practice to pick particular values that satisfy that equation under some operating conditions, because of variability with respect to the parameters and temperature, it wouldn't be critical damped for long. So it's kind of an academic study, but it allows to kind of see both the nature of the transition between the underdamped case and the overdamped case. And in addition, it allows us to see that unique form involving that additional factor of t that I mentioned. So that first bullet point is exactly what I said earlier. If you have repeated complex frequencies, your sum of two exponential term solution just becomes one, and you can't satisfy both of those initial conditions without having a contradiction. Under that form, we can actually rewrite the second order differential equation that governs the source-free RLC circuit, as you see here, and we can show that its general solution no longer will simply be the sum of two exponential terms. It will be that single exponential term, and in addition, we will have one of the unknowns multiplied by a factor of t. Now, even though the book does a nice job of showing the asymptotic behavior as t approaches infinity for this solution, even though it looks like it's going to behave a lot different, it really doesn't. And in the next module, we're going to look at a comparison of the graphs of an underdamped, critical damped, and overdamped RLC parallel circuit. But the one thing I wanted to bring up for now is if, for example, I took this figure from the text, if you take that value of R, L, and C, and you notice how precise the resistor value has to be, imagine being able to even achieve that in some scenarios in practice, what you find is that the actual response of the voltage still has that same general form that we've seen previously, namely it increases rapidly from that initial condition until the kind of asymptotic behavior of the decaying exponential starts to dominate and it converges towards zero. The key thing to point out, though, is much like the overdamped case, it never actually crosses zero. It never becomes negative. So you never have an oscillatory term in the actual response yet. That's what we're going to see in the next video. So the solution to these are very, very similar to the cases that we've already worked. So I'm going to skip doing an example for the critically damped case, and I will move on to the final case that we're going to consider for the RLC circuit, and we'll look at an additional example problem there.